Welcome to G Fun Facts Online. Today we are going to change the way you look at the ground beneath your feet. Specifically, we are going to look at the jungle floor. To the casual observer, it is just dirt, leaves, and bugs. But to a physicist or an engineer, the jungle floor is a battleground of applied mechanics. It is a place where the conventional laws of engineering are seemingly bent by creatures that have had 100 million years to perfect the art of construction. For centuries, we humans have watched ants build bridges, form rafts, and erect towers. We watched with a mix of curiosity and condescension, viewing them as biological automata. Impressive, but simple. We were wrong. Recent breakthroughs in biophysics and myrmecology, which is the study of ants, have shattered this illusion of simplicity. We are now peering into the black box of the swarm and discovering mechanisms that rival our most sophisticated machines. Foremost among these discoveries is a phenomenon that has sent shockwaves through the fields of active matter physics and robotics. It is called the Force Ratchet. This is not a mechanical gear made of steel, but a dynamic, emergent property arising from the interactions of thousands of living bodies. It is the secret that allows weaver ants to generate forces that defy the Ringelmann effect. It is the invisible engine that powers the tensile strength of ant chains, turning a fluid group of insects into a solid cable of immense power. In this episode, we are going to descend into the microscopic world of the swarm. We will disassemble the Force Ratchet to understand its gears. We will wade into the living rafts of the Amazon and climb the writhing towers of the laboratory. We will look at how these biological blueprints are already rewriting the future of robotics. This is the story of how nature solved the hardest problems of engineering, not with stronger materials, but with smarter interactions. To understand the magnitude of the Force Ratchet discovery, we must first understand a fundamental flaw in human teamwork. Back in 1913, a French agricultural engineer named Maximilien Ringelmann conducted a simple experiment. He asked individuals to pull on a rope and measured the force they exerted. Then, he asked groups to do the same. Logic dictated that a group of 8 people should pull with 8 times the force of one person. But the results were disappointing. As the group size increased, the average force exerted by each individual decreased. In a team of 8, people were pulling less hard than they did alone. This phenomenon is known as the Ringelmann effect, or social loafing. It is a coordination cost. As more agents are added, it becomes harder to synchronize effort, and efficiency bleeds away. For over a century, biology seemed to suggest that this was a universal law of collective effort. Then came the weaver ants. These arboreal architects are famous for binding leaves together to form nests, using their own larvae as living glue guns. To pull these leaves together, they form living chains, linking legs to waists, spanning gaps and hauling jagged foliage with a coordination that looks supernatural. When researchers recently hooked these ant chains up to force sensors, they expected to see the Ringelmann effect. They expected that as the chain grew longer and the team larger, the per-ant force would drop. They saw the exact opposite. In a defiance of expectations that one researcher termed a superefficiency, the weaver ants demonstrated that as the team size grew, the force contributed by each individual actually increased. A large chain was not just stronger because it had more ants, it was stronger because each ant was working harder and more effectively than it would in a smaller group. This brings us to the mechanics of the Force Ratchet. The Force Ratchet is not a magical increase in muscle power. It is an emergent mechanical strategy that separates the swarm into distinct functional roles based on their position in the chain. In a weaver ant chain, the ants are not all doing the same thing. The ants at the front, closest to the object being pulled, are the active engines. They contract their bodies, scrabbling for purchase, injecting kinetic energy into the system. However, the ants at the back of the chain do not simply pull. If they did, they might destabilize the delicate links or lose their footing. Instead, they transform into passive anchors. They stretch their bodies out, locking their joints and utilizing the friction of their foot pads to create a rigid, immovable base. They effectively store the force generated by the front ants, preventing the chain from slipping back during the relaxation phase of the pullers. This dynamic creates a ratchet mechanism similar to the tool found in a mechanics workshop. A mechanical ratchet allows motion in one direction while preventing it in the other. The weaver ant chain functions identically. First, there is the pull, where the front ants contract, moving the load forward. Then, there is the lock, where the rear ants rigidify, holding the tension and preventing the load from sliding back as the front ants reset their grip. This division of labor allows the chain to accumulate force over time. The superefficiency comes from the fact that, in a longer chain, there is more anchoring mass. The more ants you have at the back, the more force the front ants can safely exert without ripping the whole chain loose from the substrate. The group structure enables the individuals to perform at their physiological peak, uncapped by the fear of slipping. But how do they physically sustain this? The Force Ratchet operates on 2 levels, the collective and the individual. While the chain acts as a macroscopic ratchet, the individual ant possesses a microscopic one. High-resolution imaging of weaver ant anatomy has revealed a locking mechanism in the neck joint. When an ant clamps its mandibles onto a leaf or a neighbor and retracts its head, a series of ridges and latches in the exoskeleton can engage. This allows the ant to maintain a high-tension hold without constantly expending muscle energy. It is analogous to standing on a locked leg rather than holding a squat. This individual biological ratchet is the fundamental unit of the collective force ratchet. Because each ant can mechanically lock its hold, the chain as a whole becomes a structure capable of maintaining immense tension with zero metabolic cost for the anchor ants. They are not getting tired, they are simply becoming part of the geometry. While weaver ants master the art of tension, their cousins, the fire ants, are the masters of viscoelasticity. If weaver ants are the cables of the insect world, fire ants are the cement, the rubber, and the water, all at once. Originating from the floodplains of South America, fire ants have evolved to survive catastrophic inundation. When the waters rise, they do not flee, they coalesce. If you were to scoop a handful of fire ants from a bucket, they would feel like a solid ball of dough. You can toss them, juggle them, and squeeze them. They are elastic. If you press on the ball, it springs back. But if you leave that same ball on a flat surface and wait, it slowly collapses, spreading out like thick honey. If you push a penny into the mass, it sinks slowly, as if through quicksand. This dual nature, behaving as a solid under sudden shock and a fluid under sustained pressure, is known as viscoelasticity. It is a property shared by materials like silly putty and cornstarch in water. But fire ants are active viscoelastic matter. Their properties are not just passive reactions. They are actively tuned by the behavior of the swarm. The secret to this phase shifting lies in their legs. A single fire ant has 6 legs, and each leg is covered in microscopic hooks and adhesive pads. When thousands of ants gather, the number of potential connections skyrockets. In a solid state, the ants are actively gripping one another. They link their feet to form a cross-linked polymer network. This network can distribute stress instantly. When you poke a fire ant ball, the force is transmitted through thousands of leg-to-leg connections, dispersing the energy and allowing the structure to bounce back. However, these bonds are transient. Ants are living creatures. They need to move, breathe, and adjust. They constantly break and reform these connections. This turnover of bonds is what allows the fluid behavior. Under gravity, the ants slowly rearrange themselves, sliding past one another while maintaining enough connectivity to stay together. This is viscous flow. Researchers at Georgia Tech have quantified this behavior, defining the Maxwell time of a fire ant swarm, which is the timescale over which they transition from solid to liquid. For fire ants, this is a matter of seconds. Apply a force faster than they can rearrange, and they are a brick. Apply it slower, and they are a liquid. The ultimate expression of this mechanics is the fire ant raft. During floods, a colony of 100,000 ants can self-assemble into a floating pontoon in less than 2 minutes. This is not a chaotic pile of drowning insects. It is a highly engineered structure. The ants weave themselves into a multi-layered lattice. The bottom layer of ants acts as the hull. Remarkably, these hull ants do not drown. The weave of the raft is tight enough to trap a layer of air, known as a plastron, against the ants' hydrophobic exoskeletons. The raft floats not just on the buoyancy of the ants' bodies, but on this bubble of air. The force ratchet concept reappears here in a different guise. To maintain the raft's structural integrity against waves and debris, the ants must constantly exert force. They tighten their connections, effectively ratcheting the raft into a denser, tougher state when turbulence hits. When the water is calm, they relax, increasing the raft's surface area to maximize stability. Now, static structures are death for a swarm. They must be dynamic to survive. This leads us to the third pillar of emergent mechanics: treadmilling. Imagine a tower of ants. Fire ants can build Eiffel Tower-like structures to escape containers or reach hanging branches. These towers can be 30 ants high, defying gravity without any internal skeleton. For years, scientists assumed these towers were static, meaning the ants at the bottom just stood there, bearing the weight of their sisters, until the tower was no longer needed. But when researchers used X-ray videography to look inside these towers, they saw something startling. The tower was flowing. The ants at the bottom were not stationary pillars. They were slowly sinking, spreading out into the base. Meanwhile, ants from the base were climbing up the outside of the tower to the top. The entire structure was a fountain of life. A central column of sinking ants, surrounded by a shell of climbing ants. This is treadmilling. Treadmilling is a fundamental solution to the problem of fatigue and structural stability. First, it ensures load sharing. No single ant has to bear the crushing weight of the tower for long. An ant at the bottom supports a heavy load, but she slowly yields to it, sinking and spreading out. As she moves out of the high-pressure zone, she is released from duty and can climb back up to the top to become a brick once more. Second, it allows for self-healing. Because the structure is fluid, it is immune to brittle fracture. If you slice the top off an ant tower, the upward flow of ants simply replaces it. If you damage the base, the sinking column fills the void. Third, it grants plasticity. The tower can morph. If the target branch moves, the stream of climbing ants can bias their path, causing the tower to lean and grow in a new direction. This mechanism is also seen in the rafts. When a raft needs to extend an arm to grab a nearby twig, it doesn't just stretch. It cycles ants from the main body, flowing them out to the tip of the protrusion and cycling them back. The raft is a fluid machine that recycles its own parts. In the context of the Force Ratchet, treadmilling provides the reset mechanism. In a pulling chain of weaver ants, the ratchet locks force. In a tower of fire ants, the treadmill releases force, dissipating the potential energy of the load through controlled movement to prevent catastrophic failure. It is fascinating to compare these engineering strategies. Evolution is a prolific engineer, and it has designed different mechanical systems for different environmental niches. Weaver ants are the tensile architects. Their primary mechanic is the Force Ratchet, focusing on high tensile strength and low elasticity. They live in the canopy, a world of gaps and thin supports. Their chains are designed to be ropes, and ropes are incredible in tension. Fire ants, on the other hand, are the viscoelastic blobs. Their primary mechanic is active viscoelasticity and treadmilling. They need to resist compression and fluid dynamics. Then there are army ants, the living bridges. They utilize self-jamming and tensegrity. Army ants do not dig nests, they are the nest. They form a bivouac, a massive cluster of up to 1 million ants hanging from a log. When moving, they form bridges over gaps. Their mechanics rely on self-jamming, interlocking so tightly that they become a rigid solid to prioritize a stable roadway over dynamic growth. But how do they do it? There is no general ant shouting orders. There is no blueprint. The Force Ratchet, the treadmill, and the raft emerge entirely from local interactions. This is the heart of swarm intelligence. One key concept is stigmergy, the idea that the work effectively directs the work. In weaver ants, when an ant grabs a leaf, the mechanical stress is a signal. Another ant senses this tension and instinctively grabs the first ant to help. A chain forms not because they know to build a chain, but because the local rule is, if you feel tension, pull and recruit. The Force Ratchet emerges because the rear ants trigger the rule to lock their joints when pulled too hard, while the front ants trigger the rule to pull when they have footing. In fire ants, the rule is often, if you are surrounded by friends, hold on. This simple behavior creates phase transitions based on thresholds. A loose group of foraging fire ants is a gas. Shake them, adding energy or stress, and they jam into a solid. Pour them into water, and they cross a threshold to become a liquid raft. Another crucial element is the wisdom of noise. Ant behavior is not deterministic. It is stochastic, or random. Ants make mistakes. They jitter. They let go. Surprisingly, this noise is essential. If every ant locked perfectly and never moved, the structure would be brittle. It would shatter under a sudden shift. The random movements of individual ants act like thermal energy, allowing the swarm to anneal. It allows the Force Ratchet chains to readjust if the leaf tears. It allows the fire ant raft to reshape itself around a rock. The system is robust precisely because it is imperfect. The discovery of these mechanics is not staying in biology journals. It is being copy-pasted into the code of the next generation of robots. Robotics has long suffered from the Ringelmann effect. Coordinating a swarm of robots is a nightmare of communication bandwidth and latency. The Weaver Ant's Force Ratchet offers a solution: physics-driven coordination. Instead of programming robots to talk to each other, engineers are designing robots that communicate through force. We are seeing the development of an anchor-puller protocol, where simple robots are programmed with the Weaver Ant rule set. If they measure forward motion, they pull. If they measure high resistance and no motion, they deploy anchors and lock. The result is a self-organizing chain that automatically distributes the load without needing Wi-Fi. We are also seeing the birth of programmable matter inspired by fire ants. Projects like the Smarticle at Georgia Tech use simple robots that only flap their arms. Put 5 in a ring, and nothing happens. Put 100 in a box, and they jam, flow, and move like a fire ant swarm. By tweaking the activity level, researchers can make the swarm transition from solid to liquid. This is also revolutionizing soft robotics. Ants are soft, made of chitin and fluid, and this compliance is key to the Force Ratchet. If ants were rigid steel, the chain would snap. Roboticists are now building soft robots, made of silicone and pneumatic muscles, that use the Force Ratchet principle to grip objects, using friction and geometry, rather than precise motor control. Why did the Force Ratchet evolve? The answer lies in the economics of energy. For a weaver ant, a leaf nest is a castle. But leaves are heavy, elastic springs. Bending them requires immense energy. If weaver ants relied on muscle power alone, they would burn through their metabolic reserves in minutes. The Force Ratchet is an energy-saving device. By using the latch mechanism in their necks and the anchor roll in the chain, the colony converts metabolic work into structural static. They turn themselves into a clamp. A clamp holds things together for free. Similarly, the fire ant treadmilling behavior is an adaptation to the high cost of flooding. Losing a queen is game over. Losing 10% of the workers to exhaustion is acceptable, but losing the raft structure is fatal. The treadmill ensures that fresh, rested workers are constantly rotated to the high-stress perimeter of the raft, while tired workers rest in the center. It is a biological heat exchanger, but for fatigue. These mechanics are the result of an optimization algorithm that has run for millions of generations. As we look to the future, the applications grow stranger and more exciting. Imagine self-healing architecture made of materials that treadmill. If a crack forms, the material flows to fill it. Imagine nanoswarms in medicine using the Force Ratchet to mechanically drag a clot out of a vein. Imagine space exploration, where a bag of antbots uses Force Ratchet chains to pull rovers out of sand traps on Mars. The Force Ratchet is more than just a clever trick of ant anatomy. It is a profound statement on the nature of power. In the human world, we often equate power with individual strength. But the ant teaches us that true power lies in the connection. A single weaver ant is a nuisance. A chain of them is a Force Ratchet. A single fire ant is a speck of dust. A raft of them is an unsinkable ship. By studying these emergent mechanics, we are learning that the properties of the whole need not be limited by the properties of the parts. We can build strong things out of weak components. We can build intelligent systems out of simple agents. We can build solids that flow and liquids that hold weight. The Force Ratchet turns the physics of the swarm into a tool. It captures the fleeting energy of the individual and locks it into a collective legacy. As we look to the future of technology, we would do well to look down at the jungle floor. The blueprint for the next industrial revolution isn't on a microchip. It is being written in the dirt, 6 legs at a time. Thanks for listening to G Fun Facts Online.